Did you try any of these? Let's see. Pen, paper and calculator we'll need. Yeah. Say again? Oh, Matt. Good idea. You can sit beside on deck. Ready, Matt? Okay. The lowest energy level of an electron is minus 13.6 eV. The second energy level is minus 3.4 eV. So the question is, how much energy is lost if it moves from 2 to 1? So A part 1 now, that would just be the difference between the two, isn't it? So what is that? 10.2, is it? Is it 10.2? Yeah, you can put a minus in if you want. 10.2. Yeah. Oh, sorry, do you have a spare pen? Do you have a spare pen or a pencil? Yeah?
Yeah.
You can try. I'm sure I'll catch it.
No, it's out of ink.
Thanks, Matt. 10.2 eV. Now,
Did we cover up all the lecture?
Yeah.
did we? Do you mind getting that, Matt? Yeah. I think this was a morning class, was it? Yeah, you'll have to watch the video. Yeah. Okay, part 2. So this energy that's lost is lost in the form of a photon, and my question is, what's the frequency? So this is equal to HF. So if I just divide this by H, maybe one of you can give me that. 10.2 E over H. Do you have constants on your calculator and deck?
No.
No, okay. Matt, I think you do, don't you?
No, that's fine.
No, this is
No, I didn't. Not again, but can you be again?
Matt said he'll get it. E is number 23 and H is number 6. $15. Yours doesn't have these features. You're looking for the lid, is it?
No, I'm looking.
Oh, what it is, yeah.
Feels like
Seba just wants to see what your calculator's like.
Yeah.
It's from Amazon.
You got it from Amazon?
27 euro, I think.
Yeah, a little pricey. Okay. Huh? No. B part 1. So the energy here is in state 2, which has minus 3.4 electron volts, and it moves up to state 3, which is minus 1.51 electron volts. What is the frequency of the light? So it jumps up and it would need some light to give it energy to jump up. How much energy does it need? It needs minus 1.51 minus 3.4. So what's that, please? 1.91, is it?
1.89.
1.89. Went the wrong way around. Okay. So what's the frequency here? Is that it? No. Yeah, what's the frequency? So again, frequency, using the formula like we saw earlier, that this is equal to HF. So F is equal to 1.89 E over H. 4.57 times 10 to the 14 hertz. Thank you. And lastly, for question 1, when the electron is here with energy of minus 1.51 and you want to free it, how much energy will you need to give it? Yeah, you should give it at least 1.51 eV. Okay, number 2. An electron accelerated through a potential difference of 10 kilovolts. So what you have here is I need this plate to be positive, so 10,000 volts. So you get an electric field here. So what happens is the electric field, the electron enters the electric field and then accelerates out. And so the electron is moving very, very fast. And then what happens is it strikes some tungsten. Tungsten is a metal. And the work function of the tungsten is 4.5 eV. So the electron hits the tungsten and the result is a photon is released. Okay. And I think my question is, what is the wavelength of the what is the wavelength of the photon? Okay, so first thing, here it has potential energy, and here it has kinetic energy. So here's the kinetic energy, a half m v squared. Okay, and here it has potential energy. I'll just write kinetic energy. Don't write the formula out. What's the form for potential energy? No, for the other one, QED. For the electric field, QED, and we said that E is V over D, so it's QV. QV. Yeah? Now, because it's an electron, we know what the Q is. What's the Q? It's E. And we know what the V is. It's 10,000. So the energy at the beginning is 10,000 E. Now, joules. Now, you can convert that into electron volts. How do you convert into electron volts? Divide by E. So, at the very beginning, you can say the energy is 10,000 electron volts. Then this energy becomes kinetic energy. And then the kinetic energy will become the light energy here. Now you had a formula also, you had the formula Ke, what is it, is HF plus work function. Wasn't that it? Yeah? I think that was the formula, wasn't it? So basically what I'm saying is this. You have potential energy here. That then becomes kinetic energy. And that then becomes HF plus work function. Yeah?
It's KE plus work.
Oh, I have it the wrong way around, do I? So that there should be a minus then, if you move it over. Thank you. Can you see that process happening? Potential energy becomes kinetic energy becomes that. So you have 10,000 EV equals HF minus the work function. What's the work function here? Oh, it's only 4.5 EV. Yeah, so not much of a difference. 10,000 and 4.5 E equals HF. Now I don't want the F though, I want the lambda. So that's equal to HC over lambda. So I can say lambda is HC over 10,004.5 E. Okay, let's see what the lambda is. You're getting it there, Matt, is it? Minus 10 meters. 9 is nano. Oh. So it's not even nano. It's 0.124 nanometers. So part 2 or part B. Does anyone know what type of wave this is? Which wave it is on the electromagnetic spectrum? One with a really small wavelength. What could it be? Anyone want to have a guess? No? No? Good guess. Move one space left, not as far out as gamma. What was before gamma? X-ray, yeah. It's an X-ray. Yeah. What? Well, somebody's presentation. This presentation. Are you sure? Alright, okay. Okay, continue? Yeah? Continue? Question 3. A very interesting question indeed. Very interesting. Suppose an electron is in orbit of a proton and the electron is viewed as behaving like a wave. So it's behaving like a wave there in the picture. The circumference of the orbit is 2 pi r. Now, since it's moving wave-like, then the number of complete wave periods must be a whole number, since it needs to reconnect at the end. Thus, the circumference must be n lambda for some n. In the picture, n is 4. Find an expression for r using de Broglie's wave formula. So, I'll try and explain. If you look here, so here's the proton, here's the electron. Yes? But remember we learned last time that we can view this as a wave as well. So here's the proton and here's the electron as a wave. In chemistry you also called it a cloud maybe. No? You sure? Okay, whatever. So you can view it like a wave. I'll just draw a dotted line like this. Now the wave could be like this. It could go up, down, up, down, up, down, up, down, up, down. But it must finish where it starts. Okay, you can't have it like this. You can't have a wave like this. And it's broken here, like that. Okay, so if you if you can imagine you unroll the wave, the number of turns must be n. So you could have one wavelength, so it goes up, down, oh goodness, it's hard to draw this, one, one wave. Okay, it might be easier for me to draw 4 waves. Up, down, up. Up, down, up. Up, down, up. Up, down, up. So this picture here, there's 4 waves, for example. And in the picture there I gave, it's also 4 as well. So this is the electron like a wave around it. Okay. Now you know that the circumference must equal 2 pi r, because it's a circle. Yes? You also know that the circumference must equal n lambda. So for example, if this is lambda, then in the picture here there's 4 lambda. Yes? So therefore, 2 pi r equals n lambda. But you have a formula for lambda from last class. So I think we said 2 pi r equals n, and the formula for lambda was h over p, which was mv. Okay, and what am I asking you for? Find a formula for r. Okay, so now you have r equals nh over 2 pi mv. Right, so that's the first part done, A, which is find a formula for r. So you can write that down if you need to. Okay, so for part B now, I say now, the V is not known. So next, find an expression for V by using the formula from circular motion and Coulomb's law. Okay, so you know Coulomb said F equals 1 over 4 pi epsilon 0 Q1 Q2 over R squared. And also, because it's moving in a circle, you know F equals mv squared over r. So you can put these together and you can get 1 over 4 pi epsilon 0. By the way, what's Q here? What's the charge? It's an electron, isn't it? So that would be E, and the proton would be E. So that would be E squared over R squared equals mv squared over r. Right, we can cancel a bit here. I can cancel the r squared and the r there. What am I looking for? I'm looking for b. Okay, so I can say e squared over 4 pi m epsilon 0 r. That's equal to v. V is the square root of that. So v is equal to e over 2 root pi m epsilon 0 r. Okay? Yeah? Now, for part C, I tell you to put your result from B into A. So, your answer from B we put it into A. So we have R equals NH over 2 pi mv. And V is going to be E over 2 root pi epsilon 0. What letter was that there? That was an or, wasn't it? Or. Like that. Now let's clean this up a little bit. So what, I can obviously cancel my 2's. Okay. I think it would be good if we square everything. So I can get r squared equals n squared h squared pi m epsilon 0 or over pi squared m squared e squared. Now I can cancel a bit more. Cancel the or with the square there, the pi with the square there, the square with the m there. So I end up getting or equals h squared epsilon 0 over m, mass of electron that is, e squared. If I got everybody, h squared I have, I'll put in my n squared, epsilon 0 I have, e squared I have, m I have, oh I didn't get the pi here. Now do I have everybody? Yeah. Times n squared. Now, think about this. What are the possible values of n here? What are the possible values of n? If you just go back to the start, remember what n represented. So what's the possible values of n? What are the different values you could use for n? For example, could n be negative? No, it couldn't really be negative. And anyways, it doesn't really matter if it's negative because we square anyways. What could n be? What are the values? Come on, guys. Give me a break. What could the values of n be? What are the possible values for n? What are you allowed for n to be? The n? Could n be 2.5? No, because you're saying that you would have 2.5 waves. So what could n be? Yeah? Like what type of number? Yes, thank you. Thank you. N could only be numbers like 1, 2, 3, etc. Now look at what you have here, okay? You have a formula that says the radius is equal to some constant. The radius is equal to some constant times n squared. So what you've just worked out is the different radii you can have. So the first one when n is 1 is this. Then when n is 2 is this. You've just worked out the orbital radii. That's what you've worked out. The smallest possible radius is equal to when n is 1. So it'll be equal to this. Okay? So you were told in chemistry that the electrons only have certain orbits. And the orbits are exactly these orbits here we've just calculated. Now the question for the last part D is why... Okay, my question is, what idea in this question made this happen? What was the physics idea that made this situation happen? So if you go all the way back, why is it like this? It's like this because at the very beginning we said that we have to have full waves around in the orbit. Okay, we can't have, we said 1.5 wave. We have to have full waves. We have to have a whole number of waves in orbit. Because of this, and only because of this, it made the orbits have only certain values. So the reason the orbit has to be this value is so that the wave behavior finishes on a whole number. The reason it has to be this one is the same idea. You have to make sure the wave finishes at a whole number. The reason you cannot see in between is because when you try to draw your wave, you can't connect it back up. Okay, so this is the reason why you have orbitals in chemistry. The reason is because of the Broglie wave behavior of electrons. This is what forces them into different orbits. So I don't think you were told this in chemistry, right? You were just told they are in different orbits. But you've literally calculated what those radii are. So I'm not sure, but I think the smallest one when you put n equal to 1 is I think maybe about 10 to the minus 10. Do you want to check? So Matt's going to calculate there, and Siba, on your phone, could you Google something? We'll see if we're right. Type in the radius ground state hydrogen.
Radius of ground state hydrogen atom.
Yeah. Now don't say it just yet. We'll see if Matt gets the same answer. Go on, Matt.
5.29 times 10 to the power of -11.
And what's the answer?
5.2.
Okay, so, you should be pretty impressed. We've literally calculated what the smallest possible radius is. What's that called in chemistry? The S1? What's the first one? S1 is the first one, isn't it? So you've just calculated the radius for S1, the smallest radius. Yeah? Yeah? Not interesting? You don't? Yeah, okay. Yeah, okay. I think it is. I think it is. Right, okay. So, now that your mind has been blown with that, we can begin revision. So what I did this morning was I put up the latest exams, I think last year's exams. I think I uploaded 4 versions. So can you go to Moodle and just open up Moodle? You want to go to NCUK Semester 2 exams. It's going to be the first folder. I think it's going to be like 16, 17, I think. Or maybe, I might have 17, 18, yeah. Do you want to see?
Semester 2 exam?
Yeah, in physics, of course. So how many exams are in the 17, 18 folder? How many versions?
4?
There's V1, V2, V3 and V4?
Yeah.
Semester 2, right? Do you have it, Siba?
Semester 2.
Yeah.
Not on the screen there.
There's 5 versions.
5?
Yeah, 5. But
There's 5, Chow?
There's no V3 though.
Maybe.
Oh, there's 4 exams.
Yeah.
But it's V1, V2, V4, V5.
Yeah.
What?
And then you see V3.
Yeah, there's V3.
Really?
There is V3?
It's
Yeah.
not here for me. Maybe I see a signal.
Okay, are we awake? We got it?
Ah.
Okay.
No, no.
So, here's my question. How do you want to do your revision? The way you have it is two choices, okay? So here's your choices. There's only two choices because the first choice you're not going to do, because I know you guys. The first choice is you do an exam for homework, and then in the next class I do the answers, right? I'm not going to do that because I know what's going to happen. You won't do the exam for homework and you just watch me do the answers, right? Right, so that's not an option. So you don't have that option. So your second choice is you can do all of a section A and then get all the answers done by me, or we can take turns. So we could do question 1, the student does it, and then question 1 the teacher does it, then question 2 the student, and then question 2 the teacher. And you can see them. So like I might give you like 5 minutes and 5 minutes, you know. So really the choice is, do you want to do all of section A and then the answers, or do you want to take turns? And then when you finish section A, it can be B1 and then the answer to B1, and then B2, all of B2, and then the answer, and so on. So do you want to work in a block, or do you want to work one by one? Which are we thinking you would prefer for your revision? You're thinking block? What are you thinking? So we have 2 votes here. One by one? One by one? Oh, it's up to Kim, so you decide, Kim. What would you like?
Like one,
Which one?
like both.
Don't do this, Kim. Which one? Just whatever.
Do we need some points?
A coin, maybe? No.
Let's God to decide.
Well, let's see first if Kim can decide. You can't decide? Alright, we'll flip a coin then. Heads for block, tails for one by one. Okay, so heads. So it's block. Alright.
I can see the smile.
Easy way.
Easy way. Okay. So you can try section A first, and then I'll do all of section A for you. Okay. So which version? Will we just start with version 1? Let's just keep it easy and start with version 1. It's what year? 17, 18, right?